we continue from where we left off. We were calculating the pointing out how to calculate the divergence of a tensor in curvilinear coordinates. We took the cylindrical coordinates as an example. So this is done by first identifying the gradient operator, take the dot product of the tensor. So that will be dotted with the tensor has 9 components, right? And so you have terms like E, RC, RC, ERC, ERC. So we have 3 terms for the first row, and then 3 terms for the second row, which would be phi RC, phi ERC. This I call as 1. Of 2, and plus the third row can be written in terms of each tensor. The last term will be Ankit Kumar. Now, can you come forward and sit here? What we have, right? So we have to take it operation by operation. Let it act on each one of the 9 terms that are part of the tensor, right? So if I take this, we pointed out that we get terms only from the first group of terms, which is denoted as 1, right? And we get derivatives of the tensor components with respect to RC. Those are the only terms that we contribute, because you have, first of all, the unit vectors, and in fact the unit tensors, they don't depend on RC. That will considerably simplify the type of terms that come out of it. So ideally, when you have to consider the operation of this with the first row of terms, the other terms would give 0. In the same manner, the operation of this, the gradient operator equal to EZC, will give rise to terms only from the third row of terms. Right? We have seen that. And so we get actually a total of 6 terms from those 2 operations, right? 2 terms in each of the 3 directions. You can easily check that. Those would all involve derivatives of the tensor components with respect to the 3 coordinates, right? So we'll connect all the terms together at the end, but then probably the most complicated operation would involve the action of this on the 3 sets of terms, and we have already seen what its action would be for the first 2 terms. What would be the action of E phi by RC d by d phi, dotted with the third group of terms which are given by will be 0, right? If you have convinced of that, right, then there is no problem. For those of you who have not thought about it, the terms involving the derivative of the tensor components would all have E phi dotted with EZC throughout, right? So that would be 0. Now, if we look at the other 2 terms, so one of the terms would involve the derivative of EZC with respect to phi. That is 0 because EZC doesn't depend on phi, right? The other group of terms, of course, you have DERC by d phi, d phi by d phi, but for all of those terms, you would have a dot product of E phi with EZC. So that is what is in front, right? So So those would be 0. So I can conclude that this is actually 0. There will be no contribution from the third set of terms to this operation. Right? So if you now gather together all the terms involving the divergence of the stress tensor, it would be useful to write that, because I will be using it later on in the course. So if you gather together, you can compare with what we wrote down yesterday. So I will get the following three components in the direction of ERC. Plus other terms, I am not going to write them now. If we need them, we'll write it. It's going to take some time to write it, right? So this is the, you can at least check if all the terms which were coefficients ERC have been collected or not. We've evaluated all of those terms, right? So our calculation was complete today with the conclusion that the action E5 by RC d by d dotted with the third group of terms is 0. You give the 0 vector. Right? So this is what the component is, and you can easily gather together the other components. Now we will move on to calculating the Laplacian of a vector field, because that's what we need in the Navier-Stokes equation. We need to be able to solve the Navier-Stokes equation in various curvilinear coordinates, one of which will be the cylindrical coordinates, right? So now the Laplacian operator is a matrix in itself. In fact, what I will show, that to actually calculate this, we need not have the Laplacian to begin with. The Laplacian is of interest in itself, right? And so how do you calculate the Laplacian in cylindrical coordinates? I would like three ways, and I use just one of those three ways to calculate the Laplacian. So three ways. Method one would be, look at the Laplacian in Cartesian coordinates, I mean the rectangular coordinates, rectangular Cartesian coordinates, and so that would be E1, E squared. It's a scalar operator. The Laplacian is a scalar operator, so it's just E squared. The Cartesian, the rectangular coordinate would be E squared by D. That's the scalar operator. So this is actually a scalar operator acting on a vector. Now, I can consider this operator in itself, right? If I want to convert this to cylindrical coordinates, we've already got expressions for d by dx1. So all now I have to do is to get the second derivative. It's possible to express then. So these are again being expressed in terms of d by drc, d by d phi, and so on. I got that, right? We use that to actually get the Laplacian, I mean not the Laplacian, the radial operator in cylindrical coordinates. So it should not be a big problem in getting these in terms of d squared by drc squared and so on. You have to do that operation one more time. It's important for you to do it. It's not as easy as it might sound, right? It involves some care in doing this. You just leave it the simplest ways to probably look at it as an operator acting on a scalar, right? And then again you have to use the chain rule to do it. So I leave that as an exercise. It's an important exercise for you to try and do. Right now, method 2 looks at the Laplacian as actually the dot product of the gradient operator. So it looks at the Laplacian. This is a perfectly legitimate way of writing the Laplacian, and we can easily verify this in the rectangular coordinate, the rectilinear coordinates. And this is what we would get, because we know what is the dot product. It is just like a vector, dot product of two vectors, but now you have a differential operator as the components of each vector, right? That's the only difference. Otherwise, what you will need is to simply know how the dot product of two vectors is to be calculated in unit vectors, right? So I can apply the same rule. I've already got the gradient operator. So this will be ERC d by drc plus E phi by RC d by d phi plus EZC d by dzc. This would have to be dotted with the same. You have to consider the dot product of each and every one. You have to be a bit careful, because while I have this is fine, but on the other side I would have to consider the dependence of RC, ERC and E phi on phi when I carry out this. So that is another way of calculating the Laplacian. I let you do that also as an exercise. Now the method 3 is what I would use, and that I will obtain by the formula for the divergence of a vector field, which I have already got in the cylindrical coordinate. In fact, we got that as cylindrical as dBRC by drc plus drc by rc plus 1 over rc dB phi by d phi plus dzc. So I have already got that. I'm going to make use of that. So how would you get the Laplacian from this equation? What would you substitute for b? The gradient of a scalar. We know that the gradient of a scalar is a vector, right? So if I now substitute for b, the gradient of some scalar psi, right? So that means BRC is not to confuse it with the velocity. I wrote it as b. So that's what we are interested in the continuity equation. But it applies to any vector field, this formula, right? Where the components of the vector field are given by BRC, B phi and Bz. So if I do this, then BRC is simply in cylindrical coordinates, right? We already have that. So this will be d psi by drc, right? And b phi is 1 over rc d psi by d phi, and dzc is d psi by dzc. If I now substitute this into this equation, I am going to get the divergence of the gradient of a scalar, which is nothing but the Laplacian of the scalar. So from that I will identify the Laplacian operator, right? So we have this. So wherever I have drc, I have to substitute d psi by drc. So the first term would be d squared psi by d squared, right? Plus 1 over rc brc, which is d psi by drc, right? So d phi is 1 over rc d psi by d phi. So when I differentiate that and put it into this term, I get 1 over rc squared d squared psi by d phi squared plus, right, and then I substitute the final term Vzc, I get d squared by psi by dzc squared. Right? So I can from this easily identify the Laplacian in cylindrical coordinates as d squared by d. This is a very important formula, 1 over RC d by dRc. This is the operator, Laplacian operator in cylindrical coordinates. Right? Except for this term, the rest is fairly easy to remember. Right? So that's what we have. So now having got this, I can get the Laplacian of the vector field. Now what you have to remember is the Laplacian of a vector in the rectilinear coordinates is almost similar to the Laplacian of a scalar, because do you know the Laplacian, how to write the Laplacian of a scalar in rectilinear coordinates, right? Now the Laplacian of a vector can be written as the Laplacian operating on dI. However, because the EI's, the E1, E2 and E3 are independent of the coordinates, right? So I can simply write this. It's very important to understand this difference, right? The Laplacian is acting on the vector, but I can write this as the Laplacian of each component of the vector, which is a scalar, which I can directly compute from that, right? And then multiply it by the corresponding unit vector, and I get the Laplacian of the vector, which is of course a vector, scalar operator acting on a vector, and it can be easily obtained in that manner. It will be Laplacian operating on each component of the vector field will give me the value of the Laplacian of the vector field along that direction. However, if now, so this will be the first method of calculating the Laplacian of a vector field in cylindrical coordinates. You will see that it's not as simple as that, right? So to do that, one way, direct way, since I have got the Laplacian, right? I have got the Laplacian, I can do this as ERC. This is acting now on a vector field plus E5 plus EZC. Right? So I get then again, this is a scalar operator, so this will act on each one of the three terms. Right? You can see, because there is no dependence of any of the unit vectors on RC or ZC, those would be the easiest terms to evaluate. For instance, if I let this operate on the whole vector, right? This is just like in the rectilinear coordinate. This acting on this is simply going to give me, right? This alone is going to give me d squared dRC by dRC squared times ERC. That's the component I get in the ERC. This is just like operating on any one of these in the vector. Because none of the unit vectors depend on RC. So that those operations will become very easy to write down. D squared d5 by dRC squared d5 plus you can complete that d squared dzc by dRC squared dzc. It's important to see which component it contributes to, right? So I've got that. This is again very easy to write. The complication will come here, right? Now I know how to calculate the derivative of a unit vector with respect to phi once, the first derivative. What I would need are the second derivatives with respect to phi of the unit vector. You have to do it first once and then do it a second time. So you get a bunch of terms. You cannot just directly differentiate it twice, right? So clearly, one of the inputs, suppose I already know this. Clearly, you get the second derivatives. I can expect by just looking at it, the second derivatives of these unit vectors with respect to phi, because these are the only derivatives that would be of any order. So the only two unit vectors that are dependent on the coordinates are ERC and E phi, and they depend only on phi. No other variable they are dependent on, right? So clearly d squared ERC by d phi squared would be d E phi by d phi, which is minus ERC, and similarly d squared E phi by d phi squared would be minus d ERC by d phi, so that would be minus E phi. So those you would have to use and get the Laplacian. You have to do it term by term, right? So clearly the action of this on both this and this is the one that would be the most complicated to calculate, and you have to do it with some k, right? Plus making use of these expressions. So you get that let you do that as an exercise, right? Now the second, there may be more methods than what I am suggesting, and even probably shorter. You can try at least the method I am suggesting and figure out which one you think is the easiest. So the third method, or rather the second method, makes use of the fact that the Laplacian can be written as a dot product of the gradient operator with itself. So using that idea, I can write the Laplacian in this manner. Right? Now we already know what the gradient of the velocity is, calculated that, right? So now I have to calculate the divergence of that with respect to this. So one way of doing it, and in fact a very tedious way of doing this, would be to again write the a good exercise to just try and do, but it's somewhat lengthy. Dotted with, now there's no way I can just simply multiply it like I did v dot the gradient of velocity. I cannot do that trick. The simplification is not possible here. This involves a derivative, and you have to do it in the standard, because we saw that the product v dotted with the gradient of velocity can simply be obtained by pre-multiplying the matrix representation of the gradient of the velocity by the transpose of the velocity vector. Right? However, that is not possible here. So here we need to have the tensor representation of the velocity gradient tensor, and that could have, for instance, terms like dERC by dERC, ERC plus dV phi by dERC phi plus so on. So it will be a good exercise for you to please try primarily the terms involving the phi, because the others would be easy to write down. There is operation involving d by d phi on each one of these three terms. You can see how to do that. Now a third method, which is just a specialization of this, comes from the fact that I already have told you or pointed out how to calculate the divergence of a tensor. Right? Since this is also a tensor, I can directly use those formulae, provided I can identify the components of the tensor with those of the velocity gradient tensor. So in this, of course, T is just again an arbitrary tensor. It doesn't necessarily correspond to the stress tensor. I've used that because that's what it commonly appears in the equation of motion. But T is any second order tensor. And since I know that this is also a second order tensor, right? Then we can look at what that would be, right? So first I will write down what is the velocity gradient tensor in the matrix form, so that you can easily identify, right, what are the how to use those formulas, dRc by dRc. This we have already derived, right? So you can verify whether it matches with what I have written down earlier. I have this. Now, clearly, both of these methods that I am going to write, so the third method is use the formula derived for divergence of T, where T is to be equated to so this is not to be confused with the stress tensor being equal to the velocity gradient tensor. You can never accuse me of such a horrendous mistake, right? So this is T can be any second order tensor, and here I am substituting the velocity gradient tensor, right? So if you compare the methods, this doesn't require, right, any of those formulas. All this requires is the Laplacian. I can integrate this more straightforward than either of these. This is direct. Once you have the Laplacian, I can simply make it operate on the vector field and get the results, right? But however, this one requires that I have the gradient of the velocity tensor already calculated and expressed in terms of the same coordinate components, right? This further requires that I have the formula for the divergence of any arbitrary tensor already derived. If we have got all of this, clearly the most direct way of obtaining this, not most direct, is once I have got this is the simplest way to get the result. So the advantage of this method is that there is no need to, here if you see, this method as well as in this method, you will get all these components jumbled up. Finally it's a vector, right? And so we get all the components jumbled up and have to assemble them together. The advantage with this is that we already have the component of each one of the tensors written down. So directly I get together all the components. For each and every component, all the elements of each component are got directly together. There's no need to regroup them, right? But what I would suggest is, among all these methods, since I'm going to now do this one, right? It's important for you to do this. I would advise this as an exercise for you to try that. Very straightforward to do. Doesn't require any idea of a tensor or any of the unit tensors doesn't come into the picture. In that sense, it's the easier method, but you need to have the Laplacian obtained, right? So now let's take this. Let's take the what is the component in the RC direction. Let's try that. Right. So what would this be? This would be d by d RC. What would now be d RC RC? From this, what would you substitute for d RC RC? 2d RC by plus 1 over RC again. Plus 1 over RC. So which term among them? In fact, I'd like one of you to come to the board and do this, but I'm sort of ashamed to give this chalk piece to any of you. 1 by RC times 1 by RC. Yes, can you come to the board? You don't look back. 1 over RC. Now look at the board there and write first. What would you substitute for this? Basically, let me even simplify it further. First term d by d phi of, I want you to write d phi RC by looking at that, where t is here equated to the gradient of the velocity, right? Which term, right? So among there are 9 terms here, which one of the terms would correspond to d phi RC? Which one? You point out here. No, that is not d phi. Is that? Yeah, that is d phi RC. Yeah, that's correct. Yeah, you're right. d phi RC. So write that term 1 over RC, dv RC by d phi minus d phi by RC. Okay, fine. So now the next term is minus t phi phi by RC. So can you identify what t phi phi is? Here. This one, yeah. So minus 1 over RC times t phi phi, which is 1 over RC dv phi by d phi plus BRC, so there's another RC inside for each one of them, that's fine, yeah. BRC by RC. Yes. And then plus d by dzc, dzc by dzc RC, where what is that? dzc RC is that one, yeah, dvrc by dzc. Wait, dzc, yeah, that's correct. Thanks, yeah, you can go back. d by dzc of dvrc by dzc. So clearly now I can group these terms together. So first term would be d squared BRC by d RC squared with 1 over RC BRC by DRC. Now if I were to calculate this, right, so this would be, right, d squared BRC by d phi squared 1 over RC minus 1 over RC dv phi by d phi. That's what that would be. No, 1 over RC is outside. That is there. 1 over RC d squared RC by d phi square minus 1 over RC dv phi by d phi. So I am writing only the terms within the bracket. There is a 1 over RC outside. Right? Now this would be whatever it is, there is no differentiation here. So this is really d square d RC by dZc square. Right? So let's now group all of these terms together, and what you will get is the component along the RC direction of is equal to, right, I have the, this will be written as d square d RC by d RC square plus 1 over RC RC by d RC minus d RC by RC square. So these are the one group of terms plus 1 over RC square d RC by d phi square minus 2 over RC square d phi by d phi plus d square d RC by dz square. So this group of terms can be rewritten as d by drc 1 over rc d by drc of rc drc. There are 3 terms, but it can be written compactly in that manner. You can easily verify whether it can in fact be written in that manner. Okay? So now all I need to write are the other 2 components of the tensor, right? Other 2 components of the divergence of the arbitrary tensor, and then I use the fact that in that expression I put the gradient of the velocity, take the tensor and the gradient of the velocity, and I can easily get the other component. So I again let you do that as an exercise. Because all it requires, once you have the formula, right, all it requires is the substitution of the correct values of the components of the tensor, which here is the velocity gradient, and you can get all the results. Right? So finally, I mean, if you look at the continuity equation, for instance, we have exhausted. We know how to calculate the divergence of vector field. We know how to calculate the, for instance, for incomplete fluid, all we need is the divergence of the velocity field is equal to 0, right? Now, if we look at the equation of motion, so we will be largely dealing with only let's focus on incompressible. So here this is what we have. I'm just pointing out that we've exhausted all the operations we need to do to write the equations in the cylindrical coordinates, right? So we know, for instance, if we're going to write the RC component, I just have to let's also remove that. That's very easy to write down as an equation, but we are not going to consider unsteady flow for the most part of this course. So steady flow of an incompressible linear we discussed fluid, right? Then you will have minus the gradient of the pressure. So we have got the gradient operator in the cylindrical coordinates, right? Minus the gradient of the pressure, and then plus the viscosity times the Laplacian of the velocity vector. So we have got that also. We have got the Laplacian of the velocity vector. So we have all these tools required to write down the equation of motion of all the three components and against the cylindrical coordinates. And these are given in the appendices of verse stewart and line stewart. So both the cylindrical as well as the spherical polar coordinates, and we'll be using them. So what I would not only having left a whole bunch of operations to do on the cylindrical, I'm also expecting that you will at least do a few of them for the spherical polar coordinates and acquaint yourselves with these operations. And if there are any problems, we can, if you want, we can have a whole class on operations that you find difficult. We can do that as an assignment or a tutorial, right? So, are there any questions on what we have covered so far?
Finish. Stop.
Yes.